Welcome to Advanced Module 17, where we dive deep into the data center MVAC system. Today, we'll explore commissioning, heat load testing, integrated systems testing, and resilience proof. This module takes you from the design intent all the way to measured capacity, including how systems respond under controlled failure and the crucial evidence needed to ensure operations are ready. This enhanced training edition, updated for August 2026, is designed to give you a comprehensive understanding of these critical processes. In Module 17, we focus on turning installed equipment into operating proof. This means we're not just collecting startup sheets, but creating a clear, traceable argument that the entire cooling service functions reliably across normal, maintenance, and failure states. We begin by understanding key concepts like commissioning gates and who owns the evidence, as well as system boundaries and interface risks. We also cover how to select the right instruments and ensure data quality. Moving on to demonstration, we perform static tests, startup procedures, and functional performance evaluations. This includes verifying heat load capacity, stability, and heat balance, plus the system's automatic responses, recovery, and restoration capabilities. Finally, when operating, we gather evidence of tier or rated resilience, prepare standard, maintenance, and emergency operating procedures, and confirm training readiness. Seasonal and ongoing commissioning are vital to sustain performance. Remember, every claim must conclude with an observable result, a calibrated measurement, and a signed record to ensure accountability and reliability. Commissioning is really all about building a progressive evidence chain, where each step closes the risk left by the previous one before moving on to more challenging and potentially hazardous tests. We start with the design intent, establishing key documents like the owner's project requirements, basis of design, and sequencing of operations, along with setting resilience targets. Then we verify installed quality through QA/QC processes, pressure and leak tests, and ensuring cleanliness. Next, we confirm the equipment is ready through startup procedures, safety checks, and point-to-point verifications. After that, we prove the system's performance by testing capacity, controls, and redundancy measures. Following successful system proofing, we conduct integrated proof testing, which includes the high-level testing, integrated system testing, and recovery procedures. Finally, the goal is to have operations fully ready with comprehensive manuals, thorough training, and practical drills to ensure smooth and safe operation going forward. On this slide, we see that the learning route carefully follows heat as it travels from the source all the way to its final rejection point. It's important to understand that simply maintaining a stable room temperature is not enough to prove that the system is working correctly. Instead, we need to see the full thermal path and how control actions are taken at every state point along the way. Starting with the IT load or load bank, we monitor the power consumption and how heat is distributed spatially within the equipment. Next, we look at the room or rack level, checking inlet and return air conditions, including pressure and humidity. Moving further, the CRAH, FWU, or CDU units capture heat either from air or coolant. Then we focus on the hydronic loop, measuring key parameters like flow rates, temperature differences, differential pressures, and valve positions. After that, attention shifts to the cooling plant where capacity, staging, and power usage are assessed. Finally, the heat rejection stage involves monitoring ambient conditions, approach temperatures, and the operation of fans and pumps. This comprehensive approach allows us to fully understand and verify the system's performance. On this slide, we focus on the importance of using standards as a hierarchy rather than treating them as interchangeable labels. Project requirements and authority approvals ultimately control the pass or fail values, while standards provide the frameworks for process, measurement, and resilience. Starting with the reference family, local laws, standards like SNI, and authorities having jurisdiction, or AHJs, along with permits, set mandatory requirements that must always be followed. These govern safety, fire, environmental, and statutory acceptance. Keep in mind that these requirements are always mandatory, but their interpretation can vary according to the project edition and authority involved. For the commissioning process itself, ASHRAE Guideline 0 to 2019 and Standard 202/2024 lay out the framework for roles, documentation, operational requirements, and handover procedures. It's important to note that these guidelines do not define universal commissioning level names, so consistency within your project team is key. Measurement practices are governed by standards such as OSHRE's 41 series and ISO/AC 17025, which focus on calibration, uncertainty, and traceability of measurements. However, you still need to carefully review instrument range and the method of installation to ensure accuracy. For data halls and equipment ratings, standards like OSHRE TC 9.9, Standard 127, and HRI 550/590 provide guidance, but field acceptance testing must be adjusted to actual operating conditions and the specific project duty. Uptime and availability goals are set by frameworks such as Uptime Tier and ANSI TIA 942C. While commissioning evidence supports these targets, certifications are issued by the appropriate authorities. Finally, fire safety standards including NFPA 75, 92, and 2001, as well as approved fire strategies, outline critical interfaces for fire, smoke, and suppression agents. Under no circumstances should required protection be compromised simply to pass a test. Keeping these standards in their proper hierarchical roles ensures that the commissioning process is thorough, compliant, and resilient. Here we have a detailed overview of the project commissioning levels, or CXLS, which are crucial for managing risk throughout the project lifecycle. Each level is associated with specific activities and color-coded gates to clearly indicate the readiness state of the system. Starting with CXL0, the design review ensures the plans are sound before moving forward. Then at CXL1, we have the factory acceptance testing where equipment is validated before shipment. Installation is divided into two stages. CXL2A marked red for active installation, and CXL2B marked yellow indicating static conditions, signaling different levels of system readiness. Moving on, CXL3 employs the green gate during startup, verifying that the system powers on correctly. CXL4, marked blue, covers functional performance testing and high-level testing to ensure systems operate as intended. CXL5 uses a white gate during integrated system testing, which combines subsystems for thorough evaluation. Finally, CXL6 refers to handover and competency, confirming the system is ready for operation and the team is prepared to manage it effectively. Although contract names may vary, this logical progression and color coding establish consistent risk control throughout commissioning. On this slide, we focus on how governance separates key responsibilities in commissioning, HLT, and IST for the data center MVAC system. The test director controls test execution, ensuring the process moves forward smoothly, but local protection systems remain the ultimate safety authority on-site. Meanwhile, the owner takes responsibility for accepting any residual risk once testing concludes. From a technical perspective, the owner defines acceptance priorities to guide the project goals, while the engineer of record holds ownership of the design intent and any deviations that might arise. The OEM sets the equipment limits and outlines the required testing methods to maintain standards. Execution authority involves the commissioning agent, who coordinates test scripts, witnesses, and collects evidence to verify results. The general contractor manages site interfaces and resources, ensuring all elements align. Authorized personnel control critical safety procedures such as switching, permits, and lockout/tagout processes. Operational authority ensures operations personnel witness critical test scenarios firsthand and maintain ownership over standard, method, and emergency operating procedures, as well as system restoration. The owner also reviews and approves any exceptions, mitigations, or expiration of conditions. A critical point is that testing cannot begin without clearly assigned stop work authority and a named restoration owner to ensure quick response if issues arise. This governance structure keeps the testing process organized, safe, and accountable at every stage. On this slide, we focus on a crucial first step in commissioning and testing the MVAC system, defining the system boundary before you define the test. This means clearly identifying what parts of the system are included and setting clear expectations for every interface involved. Each interface must have an owner, a signal to monitor, an acceptance criterion to meet, and a restoration rule if things go wrong. We look at the main categories involved. For electrical, consider normal, standby, and emergency power. Mechanical includes equipment, pipes, ducts, and isolation components. Controls cover local safety functions, supervisory commands, and fallback options. Water and coolant systems need attention to quality, pressure class, and procedures for filling, draining, and venting. The environmental factors are equally important, such as ambient conditions and data hall boundary parameters. Finally, evidence gathering plays a vital role. This involves tracking time sources, raw data, witnesses, and file indexes to support the test outcomes. All of this defines the MVAC test boundary, where we start from an approved initial state and then introduce one controlled disturbance to evaluate the system's response. This structured approach ensures clarity and accountability throughout the commissioning process. On this slide, we're focusing on how backward planning is crucial for protecting the HLT and IST windows during commissioning. The key idea is that readiness isn't just something you scramble to achieve at the last minute. It's built starting from the service date and working backward. This way, everything like scripts, load banks, trend points, witnesses, and even retest allowances can all line up perfectly before test week. Starting at T-120 days, we outline scenarios and set up temporary works. By T-90 days, draft TMS, points, and load schedules are ready. At T-60 days, it's time to confirm instruments and power paths. Then, by T-30 days, we have approved scripts and perform trend rehearsals. Moving closer, at T-7 days, readiness is checked daily with a go/no-go decision. During test week, we execute tests, restore systems, and compile reports. Finally, at T+45 days, stabilization takes place alongside closing out any remaining issues. This structured approach ensures a smooth and well-coordinated commissioning process. On this slide, we're focusing on the importance of a test pack being reproducible. The key idea is that another competent engineer should be able to safely repeat the test and arrive at the same decision just by reviewing the record. To ensure this, a test pack must clearly outline several critical components. First, the purpose, which includes the design intent and boundaries of the test. Then, the prerequisites like tags, the issue status, and any necessary permits. Next comes the initial state, detailing the system topology, load conditions, set points, and any alarms present. The method follows, describing the specific actions taken, expected results, and exact timestamps. Accurate data collection is essential, involving manual readings, trends, and raw data exports. After that, the decision criteria come into play, highlighting acceptable deviations and when a retest might be needed. Finally, the restoration phase ensures the system is returned to an as-left state, complete with sign-off, so the entire process is thoroughly documented and reproducible. Safety and abort criteria are a crucial part of the engineering method when conducting tests. The test must be stopped immediately if personnel safety, life safety, critical load stability, or evidence integrity are at risk. Before starting, we ensure there is an approved risk assessment and method in place, proper lockout/tagout procedures, clear switching boundaries, and controls for temporary power, cables, and hoses. Emergency communication plans and exclusion zones are also established to protect everyone involved. During the test, if there's any personnel or life safety risk, uncontrolled thermal or hydraulic events, unexpected critical load instability, or loss of monitoring that compromises the results, we abort right away. After aborting, we return to a safe, protected lineup, preserve all raw data and event chronology, and then raise the issue to identify the root cause and responsible party. Only after a revised method is approved can we proceed with retesting. This process ensures safety and reliability at every step. On this slide, we see how a single time base is crucial for turning multiple logs into one clear event narrative. It's important that all the systems involved, like the building management system, control points, emergency power management system, loggers, power quality monitors, video recordings, and even manual sheets, are synchronized. They need to agree on exactly when the trigger, response, and recovery happened. We start with the physical trigger, which can be either a device or a controlled simulation. Then, the controller plays a key role by providing command signals, feedback, and permissive conditions. The operational technology network must ensure reliable paths, redundancy, and precise timestamps. Next, the platform records alarms, trends, and sequences of events. The operator's role includes acknowledging alarms and approving actions taken. Finally, all raw evidence files are indexed and linked to specific test steps, creating a complete and verifiable timeline of events. This alignment is essential for accurate commissioning, testing, and troubleshooting in a data center environment. When selecting instruments for testing, it's crucial to choose devices that not only collect data, but also truly prove the claim being made. The range, response time, installation method, and calibration status of each instrument must align with the specific variable and event you're testing. For example, an ultrasonic flow meter is ideal for measuring liquid flow and performing heat balance calculations. Point 100 sensors and data loggers are used to monitor supply, return, and rack temperatures accurately. Differential pressure manometers come into play for testing coils, filters, rooms, and door pressure. To measure air velocity and volumetric flow, we use anemometers or hoods. Power analyzers help us capture kilowatt load, power factor, harmonics, and event data effectively. Thermal cameras and vibration meters are excellent for screening abnormal conditions. It's also essential to document and retain the instrument ID, serial number, range, accuracy, calibration certificates, and exact test position for every accepted result to ensure traceability and reliability. Always verify that the equipment used on site matches the approved setup, including ratings and test boundaries, before proceeding. Here we see how the measurement plan connects each variable to its preferred field method and the typical evidence required. This is critical because every selected method must be verified to fall within the approved project tolerances and the instrument manufacturer's application limits. For example, when measuring water flow, a calibrated inline meter or a clamp-on ultrasonic with a verified straight run is used, and evidence like raw flow data, pipe and fluid details, signal quality, and a location photo are collected. Temperature or delta T measurements rely on matched calibrated RTDs, or thermistors placed in representative wells, with evidence including channel mapping and before and after stabilization checks. Airflow measurements use traverses, capture hoods, or calibrated arrays with density correction, supported by data such as traverse points and averaged results. Pressure or differential pressure is monitored using calibrated transducers with proper zero checks and tubing arrangement verification. For power and energy, revenue-grade meters with verified CT and VT scaling provide waveform files and synchronized data for analysis. Lastly, vibration measurements involve accelerometers mounted at defined bearing locations, with evidence on speed, load, axis orientation, and mounting method following OEM or ISO criteria. This comprehensive approach ensures accuracy and reliability across all key variables in the commissioning process. Calibration traceability is essential, but on its own, it doesn't guarantee accurate or reliable test results. Having a valid certificate within its validity period and ensuring the laboratory's competence with a traceable reference are fundamental components of traceability. It's also crucial that the instrument ID matches the field device, and that both the as found and as left status are thoroughly recorded. However, fitness for purpose goes beyond these basics. For example, accuracy must be precise enough to resolve the acceptance band, while the measurement range must prevent overload and maintain good resolution. The response time needs to be fast enough to capture the relevant event properly, and the environmental rating of the instrument must be appropriate for the actual test location. In addition, field control measures like zero and reasonableness checks, using matched sensors for small temperature differences, and having an independent reference when risks are high, all strengthen the reliability of the calibration. Finally, performing a post-test drift check is vital for critical measurements to ensure stability over time. So, while traceability is necessary, it's just one part of a comprehensive calibration strategy. On this slide, we focus on how to handle measurement uncertainty when dealing with narrow margins. The key method here is the root-sum-square approach for combining independent uncertainty contributors. This helps us calculate the relative heat uncertainty by considering uncertainties in flow, temperature difference, density, and specific heat capacity. For temperature, we look at matched channels, combining supply and return temperature uncertainties to get the overall delta T uncertainty. When making decisions, it's essential to apply a guard band, meaning we only pass the measurement if the result plus its agreed uncertainty falls within the acceptance criteria. In this example, the flow uncertainty is plus or minus 1%. Delta T uncertainty at 10 Kelvin is about 0.4%, and when combined, the total relative uncertainty comes to approximately 1.1% before factoring in coverage and other minor contributors. This thorough approach ensures we make reliable judgments even when margins are tight. On this slide, we focus on the core commissioning equations that link load, flow, temperature, and power in our data center MVAC system. It's essential to use a consistent unit system and keep the fluid property basis throughout all calculations to maintain accuracy. Starting with the waterside heat, represented by Q, which equals the density times specific heat capacity, volume flow rate, and temperature difference. Similarly, airside sensible heat is calculated with the same principles, but using air properties. The energy balance error helps us assess discrepancies between water heat and the load, expressed as a percentage. The available margin tells us the difference between what's available and what's actually tested. We also consider response time, measuring the delay between the trigger event and when conditions stabilize. Finally, for thermal energy storage, usable energy is integrated over time based on these parameters. Remember, acceptance depends not just on meeting numerical criteria, but also on the operating state that produced those results. Here we have a worked example showing how to reconcile electrical heat with hydronic heat capture in a data center MVAC system. Starting with the load bank heat, the electrical input is 2,000 kilowatts. The measured water flow rate is 48.5 liters per second, which converts to 0.0485 cubic meters per second. Moving on to water temperatures, the chilled water supply is at 16 degrees Celsius, and the return is at 25.8 degrees Celsius, giving us a temperature difference of 9.8 Kelvin. Using these values, we calculate the hydronic heat captured as approximately 1,984 kilowatts. The balance error, which compares the hydronic heat to the electrical input, is just 0.8%. This shows a very close match. However, this heat balance is only credible after we carefully review factors like instrument uncertainty, auxiliary heat gains or losses, and any stored energy effects that might impact the measurements. It's important to replace the example inputs and tolerances with approved project-specific data to ensure accuracy. Before any switches or valves are moved during commissioning, it's crucial to write clear acceptance criteria. Each criterion should include specific elements: the variable to be monitored, the limit it must stay within, the duration it must be maintained, the operating state, the evidence needed, and who has the authority to make the decision. For example, the initial state criterion requires the plant to be in an approved normal lineup with stable trends and no unapproved overrides. This prevents starting off on the wrong foot and avoids invalid conditions. The performance criterion ensures the system achieves the required duty under declared ambient and load conditions, linking the outcomes directly to the design intent. Stability means the controlled variable stays within an agreed band for a defined soak period, which helps distinguish between short-term success and true steady operation. Failure response criteria verify that backup systems activate automatically without cascades, with proper alarms and fallback measures. This proves the system's resilience, not just its capacity. Restoration criteria confirm that normal operations return without lingering alarms, overrides, or instability, preventing latent defects caused by testing. Finally, evidence gathered includes raw data, screenshots, readings, photos, and signatures tied to each step, ensuring that all decisions are fully auditable. This thorough approach helps guarantee reliable commissioning and safe operation. On this slide, we're focusing on the process for handling issues, deficiencies, and exceptions during commissioning, HLT, and IST activities. It's crucial to understand that despite any schedule pressure, missing safety measures or invalid evidence can never be accepted as an acceptable condition. The process begins by raising and recording the issue and gathering all relevant evidence. Next, we classify the problem, whether it's a deficiency, a commissioning issue, or a safety stop. After classification, we assess its impact on safety, validity, and system resilience. Then, we assign an owner, set a due date, and determine the appropriate project gate for resolution. The next step is to correct the issue with an approved action. Once corrected, retesting is performed using the same criteria to ensure traceable evidence. Finally, after all steps are satisfactorily completed, the issue is formally closed through authorized acceptance. This rigorous path helps us maintain the highest standards and safety throughout the commissioning process. Here we're focusing on Section 01, which covers pre-commissioning and static verification. This phase is all about ensuring that the systems are clean, pressure-tight, and maintainable before any rotating equipment is allowed to start. Getting this right is crucial because it sets the foundation for safe and efficient operation down the line. It helps prevent issues that could arise from contaminants or leaks and ensures everything is in proper working order before moving forward. This slide emphasizes that installation quality is the foundation for reliable performance data later on. Before covers and insulation go on, thorough inspection is critical to address several key risks like access, orientation, support, isolation, and maintainability. For equipment, we need to verify the nameplate matches approved submittals, ensure proper orientation, level installation, secure anchoring, and adequate vibration isolation. Service clearances must be sufficient, and we should confirm clear routes for lifting and removal. Transit restraints need to be removed, and internal components must be clean. When it comes to pipes and ducts, supports, expansion joints, and flexible connections must be properly installed. Flow direction should be correct, and necessary vents, drains, and test points must be in place. It's crucial to use the right pressure class and materials for safety and performance. Fire-stopping details, access panels, and insulation interfaces also require careful attention. For controls and safety, sensor and actuator locations must be accurate, cable separation and grounding correctly done, and all labeling clearly visible. Finally, access to local isolators and emergency stops, as well as leak detection and containment pathways, need to be confirmed. This thorough inspection process ensures that once the system is covered up, no hidden issues compromise future operation or data integrity. On this slide, we focus on the crucial process of pressure and leak testing, which is designed to prove system integrity without causing damage. It's essential that the test medium, pressure levels, duration, and any exclusions strictly follow the approved methods and component ratings to ensure safety and accuracy. When planning the test, you need to clearly define the test boundary and isolate the correct components. Make sure relief devices and vulnerable elements are verified and use calibrated gauges placed at representative points. Also, don't forget to factor in any elevation or temperature changes that could affect the test results. During execution, fill and vent the system slowly, allowing it to stabilize before starting the timed hold. Carefully inspect all joints, valves, hoses, and equipment for leaks. Record all observations for pressure, temperature, and any leakage. When closing, repairs must be done under controlled depressurization and the affected boundary retested. Finally, drain, dry, or preserve the system as required, then issue a signed certificate and a marked-up boundary for documentation. Remember, pneumatic tests involve higher risks, so they should only be used when specifically approved. On this slide, we're focusing on the flushing process during commissioning, which is crucial for protecting sensitive components like coils, plate heat exchangers, CDUs, control valves, and pump seals from contamination. The process starts by mapping the system's loops, dead legs, and temporary bypasses to understand where debris might accumulate. Next, we prepare the system by removing or protecting any sensitive equipment and installing temporary strainers. Then comes the flushing itself, where we ensure an approved velocity and sequence to effectively remove debris. After flushing, we inspect strainers, take samples, and check for turbidity or particle evidence to assess cleanliness. This cycle is repeated until the cleaning criteria are stable, ensuring that no contaminants remain. Finally, we restore the system by installing the final strainers, valves, vents, and setting everything back to the as-left lineup. This thorough approach ensures that the system is clean and protected before startup. On this slide, we focus on the importance of water chemistry acceptance in protecting heat transfer efficiency and overall system reliability. The key idea here is that treatment targets must be tailored based on several factors, including the metallurgy of the components, the type of fluid used, whether the system is open or closed loop, and specific requirements set by the original equipment manufacturer. For closed chilled water and total cooling systems, critical parameters include maintaining the correct pH levels, monitoring conductivity, and ensuring the right concentration of corrosion inhibitors. It's also essential to keep an eye on glycol concentration when freeze protection is necessary, as well as dissolved oxygen levels to manage corrosion risks. Additionally, controlling microbiological growth in solids helps prevent fouling and degradation. In open condenser water systems, we pay close attention to cycles of concentration and conductivity to prevent scale and corrosion. Implementing an effective biocide program is vital for controlling microbiological activity. Proper management of makeup water, blowdown, and drift also plays a crucial role in maintaining system integrity. Supporting evidence for proper water chemistry includes baseline laboratory certificates, accurate dosing calibration, and maintaining a chemical inventory. Building management system alarms linked to conductivity and blowdown operations provide real-time alerts. Finally, marking trend and sampling locations clearly on system schematics ensures consistent monitoring and helps catch any issues early on. On this slide, we're focusing on the commissioning of pressurization, expansion, and air removal as a single hydraulic function in data center MVAC systems. It's crucial to understand that an incorrect vessel precharge or trapped air can mimic pump, valve, and control faults, which can lead to misdiagnosis and system inefficiencies. We start with static checks, verifying vessel size, connection, and precharge, as well as cold fill pressure at the connection point. We also check the relief path and discharge termination for proper setup, along with ensuring the degasser or air separator is correctly located and accessible for service. Moving on to functional checks, we test duty and standby pressurization pumps, monitor low and high pressure alarms, and confirm makeup interlocks are operational. We assess expansion across the full temperature range and verify air removal at high points and low velocity zones to prevent issues. For acceptance evidence, we look at pressure trends from cold conditions to operating temperature, review pump run and rotation records, and examine the vessel precharge sheet. All of this confirms that there is no cavitation, nuisance relief, or uncontrolled makeup, ensuring the system operates reliably and efficiently. On this slide, we focus on the critical need for functional proof of insulation, trace heating, and vapor sealing in chilled and coolant systems. Even if the installation looks visually complete, hidden issues like condensation, thermal bridges, or inactive protection circuits can still pose significant risks. Continuous vapor barriers and properly sealed penetrations are essential to prevent moisture intrusion. It's important that insulation is of the correct thickness, and that valve and strainer boxes remain removable for maintenance access. We also need to conduct surface temperature and condensation surveys at the worst dew point conditions to catch potential problem areas early. Identification labels must stay visible and serviceable throughout the system's life cycle. For freeze and process protection, ensuring circuit continuity and insulation resistance is crucial. This includes checking thermostats, low temperature initiations, alarm signals, and BMS status. Finally, pay attention to power loss behavior, proper labeling, and easy access to junction boxes to ensure the system remains reliable and maintainable. On this slide, we're focusing on the critical process of hydronic TAB, which must prove the design flow at the hydraulically demanding point. This means balancing with the control valves set in their intended operating mode, while maintaining the pump speed, differential pressure, and valve authority. The pump operating point is assessed by plotting the measured flow and developed head on an approved pump curve, ensuring the pump performs as expected. For the coil or CDU branch, we monitor the flow, entering and leaving temperatures, valve command, and measured differential pressure to verify proper function. Valve authority is a key concept here, calculated as the ratio of the valve pressure drop to the total pressure drop of the branch. This indicates how much control the valve has over the flow. Finally, system proof requires that the remote branch meets its duty without causing instability in other branches. It's important to remember that project tab tolerances typically allow for plus or minus 10%, but this should never be assumed without formal approval. This ensures precise and reliable commissioning of the system. Airside pre-commissioning starts with ensuring that all pathways are clean, accessible, and properly sealed. This is crucial because any defects in ductwork or containment can significantly alter the measured airflow, and may also mask underlying issues with fans or coils. We need to focus on the internal cleanliness and construction class of the ductwork, along with performing leakage tests according to approved pressure classes. Flexible connections, supports, and access doors must be checked for integrity. Fire and smoke dampers need to be accessible and clearly identified for safety and functionality. Additionally, equipment interfaces need careful assessment. Filters must be installed correctly, and the differential pressure sensing should be accurate. Coils should be clean, with drain pans and traps properly completed to avoid any water issues. Fan guards, rotation clearance, and isolation are essential for mechanical safety. Sealing at floor and wall junctions is important to prevent air bypass. We also must manage the boundaries in the data hall carefully. Raised floor openings should be controlled, containment doors and panels aligned, and any blanking panels or cable openings properly sealed to maintain air containment. Lastly, defining clear pressure reference points helps in accurate measurement and control throughout the commissioning process. Getting these details right ensures a reliable and efficient airside system from the start. On this slide, we focus on the critical aspect of airflow testing in data center MVAC systems. Airflow testing must always follow a declared method and be based on an accurate density measurement. It's important to remember that one-point velocity readings can't replace a full, representative traverse or a calibrated capture method. We calculate volumetric airflow by multiplying the cross-sectional area by the average velocity, while mass airflow is the product of air density and volumetric airflow. For sensible cooling calculations, we use the mass airflow along with the specific heat capacity of air and the temperature difference between return and supply air. Fan performance relationships show us that flow varies proportionally with speed. Pressure changes with the square of speed, and power consumption increases with the cube of speed. This is key when operating within a similar speed region. Lastly, it's essential to record the traverse grid, the free area, air density, fan speed, and instrument orientation to ensure accurate and reliable airflow measurements. On this slide, we're focusing on the importance of condensate testing to confirm proper drainage under real pressure conditions. A dry pan during inspection alone isn't enough to prove that the trap, slope, leak alarm, and disposal route are all functioning correctly. We start by thoroughly inspecting several key components: the pan slope and corrosion protection, the trap geometry as it relates to the unit pressure, cleanouts, vents, and access points, plus pipe support, fall, and termination. Next, we conduct tests by introducing controlled water into the pan, operating the fan at the relevant pressure to mimic actual conditions, and verifying that the drain runs continuously without any airlocks. We also simulate high-level or leak alarms to make sure the system responds accurately. Finally, acceptance criteria include no overflow, leaks, or standing water, proper alarm activation identifying the correct unit and zone, the drain route avoiding sensitive equipment, and restoration of the trap seal with all evidence properly recorded. This comprehensive approach ensures the condensate system works reliably in real-world operation. On this slide, we're focusing on the critical steps for commissioning DX and VRF circuits, emphasizing that these systems require thorough refrigerant, drainage, and control verification. It's essential to always follow the OEM procedure and adhere to local refrigerant safety standards rather than assuming the refrigerant charge is correct based solely on compressor startup. Starting with the static phase, verifying pipe materials, their supports, and branch orientation is fundamental to ensuring system integrity. Equally important are pressure and leak testing, along with dehydration records, to confirm the circuit is free of contaminants and moisture. Proper insulation and vapor sealing help maintain system efficiency and prevent condensation issues. And don't forget to confirm refrigerant quantity and maintain cylinder traceability for accountability. During startup, you need to check compressor and fan rotation and current to avoid mechanical damage. Assess superheat and subcooling values against OEM diagnostics, and verify that high and low pressure safeties and temperature safeguards are functioning correctly. The operation of the condensate pump and leak alarm should also be confirmed to prevent water damage. Finally, performance verification is vital. Confirm the unit's capacity matches declared indoor and outdoor conditions, and ensure staging and part load stability for efficient operation. Test unit or network failure scenarios and restart functions, and validate alarm routing along with remote and local control capabilities to guarantee system reliability and responsiveness. These steps are key to a successful commissioning process that ensures the system operates safely and efficiently. Following them diligently helps avoid future issues and extends the lifespan of the equipment. Now we're moving into Section 02, where we'll focus on equipment functional and performance testing. This section covers a variety of key components including chillers, pumps, airside units, heat rejection systems, thermal energy storage, plate heat exchangers, and liquid cooling, all tested under their actual measured duty conditions. Understanding how each of these performs in real-world scenarios is critical to ensuring system efficiency and reliability. This slide covers the role of the Chiller Factory Acceptance Test, or FAT, in establishing a frozen baseline for performance and control as it leaves the factory. The key idea here is that factory evidence should significantly reduce site risk, though it doesn't eliminate the need for integration tests on site. We begin with configuration details, including the model, serial number, refrigerant type, and compressor specifications. This ensures the product matches the approved selections and accessory requirements. Firmware, settings, and communications protocols are also confirmed. Electrical ratings and harmonic mitigation measures are verified to comply with standards. Witness tests are a critical part of FAT, where capacity and efficiency are checked at agreed performance points. Water pressure drop and flow are proven, along with the functionality of safeties, alarms, and interlocks. The system's staging, unloading, and restart behavior are observed to confirm proper operation. The release dossier compiles raw data and corrected results, accompanied by calibration certificates and test stand details. Any punch list items are addressed and retested, finalizing the as-shipped settings. Finally, preservation, lifting, and site checks ensure the chiller arrives ready for installation without damage or disruption. This thorough process gives us confidence in the equipment before it even reaches the site. This slide highlights the critical steps for a successful site chiller startup, which is essential to close installation and integration risks. We must ensure that the startup only happens after confirming key prerequisites like flow, water quality, power, controls, and heat rejection are all verified. The process begins with the pre-start checks, focusing on flow switches, strainers, isolation, and power quality. Next, we address auxiliaries such as heaters, oil and lube systems, pumps, and fans to make sure everything supports operation. The first start involves monitoring rotation, pressures, temperatures, and current to confirm the chiller runs correctly. Safety is also crucial. We simulate approved trips and interlocks to ensure the system responds properly during faults. Controls are tested both locally and remotely, with set points and integration into BMS or CPUS verified. Finally, we establish a baseline with stable data and finalize as-left settings, ensuring the system operates optimally and reliably moving forward. On this slide, we focus on the Chiller Field Performance Test, or FPT, which is critical for proving the chiller's capacity, efficiency, staging, and recovery. The key is to take correct measurements according to the approved rating method, but we also accept performance based on the project's declared field duty. We start by verifying the minimum stable load, monitoring chilled water flow and temperatures, compressor state, and power. It's important to ensure there are no hunting behaviors, nuisance trips, or unstable leaving water control, as these affect reliability. Next, testing at various duty levels, 25, 50, 75, and 100%, helps us measure capacity in kilowatts and check ambient and entering condenser conditions. These measurements are compared with an approved corrected baseline to assess efficiency truly. We also check lead and lag operations, including enable logic, timers, starts, and run hours, to confirm the sequencing is correct and prevent short cycling. During a chiller failure test, alarms, standby starts, chilled water supply excursions, and recovery are verified to ensure required duty is maintained without unwanted cascade effects. Finally, power disturbances are simulated to test ride-through, restart timelines, alarms, and the approved restart order, ensuring stable controls and a safe recovery process. This thorough testing guarantees the chiller performs reliably under all expected conditions. On this slide, we focus on the importance of clearly declaring the ambient and correction basis when reporting air-cooled chiller results. A field test conducted under specific conditions, like those in Jakarta, is only valid if the operating envelope and the normalization method are explicitly stated. It's not reliable to compare results directly to a standard rating point without context. For measured capacity, we use the formula Q equals density times specific heat times chilled water flow rate times the temperature difference of chilled water. When it comes to efficiency, the coefficient of performance, or COP, is calculated by dividing the cooling capacity by the electrical power input. It's critical to record the dry bulb temperature at representative condenser air inlet locations to establish a solid weather basis. For corrections, always apply an approved method from the OEM or AHRI. Avoid creating your own linear ambient corrections. Finally, before blaming any capacity shortfall on weather conditions, make sure to check for condenser air recirculation and coil fouling, as these factors can significantly impact performance. On this slide, we focus on the critical process of pump startup, which ensures that all mechanical, hydraulic, and protective functions are operating correctly. Before a pump is accepted, we must confirm that suction conditions, flow rates, head pressure, power consumption, and vibration levels are credible and within specifications. We begin with the static checks and the initial start, verifying alignment, base stability, pipe strain, and the presence of guards. It's essential to confirm proper priming, venting, and rotation direction to prevent damage. The valve lineup and establishing a minimum flow path are also key steps. Monitoring seal, bearing, and lubrication conditions helps us avoid premature failures. We take detailed measurements including suction and discharge pressures, differential head, flow, speed, and variable speed drive commands and feedback. Electrical parameters like voltage, current, kilowatt usage, and power factor are carefully observed. Vibration monitoring is conducted at defined bearing points along each axis to detect any anomalies early. Protection systems such as low flow, dry run, and overload safeguards must be tested and confirmed operational. Lead and lag pump sequences and automatic standby functionalities are verified to maintain system redundancy. Finally, we ensure controls can switch between remote and local modes seamlessly, handle communication loss effectively, and properly trigger alarms with reset and return to service capabilities. This comprehensive approach guarantees that the pump is fully ready for reliable service in the data center MVAC system. On this slide, we're focusing on how to plot the measured pump point against the approved curve. The key is that the operating point must deliver the required flow at the system head while avoiding any issues like unstable operation, cavitation, or overload. When interpreting the plot, the measured duty point is found where the pump's performance curve intersects with the system curve. It's important to repeat this process for both the minimum and maximum credible configurations to ensure reliability across conditions. Also, when dealing with parallel pumps, we need to ensure stable load sharing and validate performance without relying on non-return valves. This helps maintain system stability and efficiency. On this slide, we focus on how CRAH and FWU testing connects coil hydraulics directly to rack inlet conditions. The key point here is that the entire system, from the unit and control valve to the fan modules, containment boundary, and data hall sensors, works as one integrated test system. We start by confirming the status of filters, coils, drain pans, traps, and leak detection to ensure everything is intact. Next, we measure critical variables like water flow, the temperature differential or delta T, and valve command and feedback to monitor system responsiveness. Simultaneously, airflow, pressure profiles, and fan speed are tracked to maintain optimal operating conditions. It's equally important to trend rack inlet temperatures, return air conditions, humidity, and pressure to understand environmental impacts. We also perform tests to detect fan module loss, unit loss, and network fallback scenarios, which helps maintain system resilience. Another crucial aspect is verifying the service replacement mode works properly without exposing any moving parts, enhancing safety. Ultimately, the acceptance criteria hinge on achieving the protected thermal outcome, combined with the automatic control actions that delivered it. Finally, the setup must be verified on site to match approved equipment, ratings, and test boundaries to ensure everything conforms to specifications. This slide highlights the importance of using simultaneous airside, waterside, and control data when commissioning CRAH and FWU FPT systems. Collecting only one variable at a time can lead to missing critical issues like bypass air, low delta T, or control interactions that affect system performance. We focus on several key functions here. First, primary measurements include airflow, water flow, entering and leaving temperatures, and fan power. These are essential to ensure the system meets the required sensible capacity under declared room and water conditions. Next, pressure control involves monitoring room or aisle differential pressure, fan speed, and damper or containment states. The goal is to maintain stable pressure without excessive leakage or hunting. Valve control is equally important, with measurements like PICV commands, flow rates, and coil delta pressure to maintain stable leaving air and room conditions across the entire load range. Module redundancy is monitored through fan status and airflow profiles to ensure the loss of a single module doesn't cause unacceptable hot spots. Finally, condensate and leak detection use pans, traps, leak cables, and alarms to guarantee correct zone drainage, prevent overflow, and trigger safe responses when needed. All these data points working together provide a comprehensive picture needed for effective commissioning and ongoing system management. In this test, we simulate a failure by tripping one duty fan module or an entire unit using the approved method. The key point is that the system must detect and correctly identify this failure. Then, the remaining units or modules should increase their output, but only within approved limits to maintain stability. It's crucial that group control or local fallback remains stable, preventing any unacceptable temperature changes at the rack inlets. We also need to watch out for potential issues like fan backflow through the failed module, any single-point failures in the network controller, valve or fan hunting, and hidden hot spots that might not be detected due to averaged room sensors. Evidence for the test includes monitoring fan commands and feedback, the rack inlet sensor grid, chilled water flow and temperature difference, as well as the alarm and recovery timeline. The test is accepted if the protected zone stays within the project's thermal limits and the system restores itself without any lingering overrides or alarms. On this slide, we're focusing on the critical aspects of heat rejection commissioning, which includes water treatment and how weather impacts the process. Depending on the tower type, the test methods vary, but every system must demonstrate effective heat transfer, proper fan and pump control, maintained water quality, and a reliable response to cell failure. For open-circuit systems, we pay close attention to components like the basin, fill, nozzles, drift, makeup water, and blowdown. Closed-circuit systems require monitoring of the coil, spray loop, freeze protection, and glycol quality. Hybrid or adiabatic systems introduce a dry-to-wet transition phase, along with pad and spray uniformity and proper drain down. It's essential to record ambient conditions such as dry and wet bulb temperatures, entering and leaving water temperatures, flow rates, and fan speeds. Additionally, testing includes cell isolation, standby response, and strategies for water loss fallback. We also need to inspect access points, vibration levels, plume behavior, recirculation, and ensure safe chemical handling practices. One key point is that the approach temperature is only meaningful when referenced against the correct ambient wet bulb or dry bulb temperature for the specific equipment type. Finally, setting up the test correctly means verifying the actual approved equipment, their ratings, and the boundaries of the test on site. When evaluating cooling tower performance, it's crucial to compare it against accurately measured ambient conditions. To do this effectively, you need to use representative ambient instruments that are placed away from discharge recirculation and solar bias to ensure reliable readings. One key metric is the range, which is the difference between the entering water temperature and the leaving water temperature. Another important measure is the approach in an open tower, defined by the difference between the leaving water temperature and the ambient wet bulb temperature. Heat rejection is calculated using the formula Q equals density times specific heat capacity times the flow rate of the cooling water times the range. Monitoring cell performance involves recording fan speed, pump flow, basin level, conductivity, and makeup or blowdown rates. If you observe a high approach, it often indicates issues such as airflow recirculation, fouling, poor water distribution, low flow, or incorrect wet bulb temperature measurement. Understanding and monitoring these factors helps maintain optimal cooling tower efficiency. On this slide, we're focusing on commissioning dry and hybrid coolers, which require thorough mode transition and freeze protection proof to ensure reliable operation. The key point here is to commission the actual sequence, which includes dry mode, adiabatic or wet assist, drain down, and failure fallback. In dry mode, we need to verify fan staging, control of leaving fluid, and performance under minimum ambient conditions. We look at fluid temperatures, ambient dry bulb temperature, fan speed, and power consumption as evidence. When using adiabatic assist, it's critical to confirm permissives like when it's appropriate to activate, ensure wetting uniformity across the pads, monitor water quality, and evaluate effectiveness. Measurements include dry bulb and relative humidity, pad and spray status, water flow, and approach temperatures. If water becomes unavailable, the system must safely fall back without uncontrolled thermal excursion. We confirm this through alarms, mode changes, capacity measurements, and recovery trends. Freeze protection involves checking glycol concentration, heater or trace heat function, proper drain down, and alarm operation. Evidence here comes from lab results, temperature simulations, and valve functionality tests. Finally, in case of cell or fan failure, the system should maintain remaining capacity without cascading failure. We monitor status, temperatures, controller sequences, and restoration procedures to prove this. Each of these steps is crucial to ensure the data center MVAC system performs reliably under all operating conditions. On this slide, we're focusing on the critical testing requirements for both the plate heat exchanger, or PHE, and the thermal energy storage, TES systems. Accurate temperature measurements on both sides of these systems and throughout the stored volume are essential. These measurements help us evaluate three main aspects: the heat exchanger performance, tank stratification, and pump or valve control. For the PHE, we need to monitor flow rates, inlet and outlet temperatures, and pressure drops on both circuits to understand how well the heat exchange is functioning. For TES, temperature sensors must be placed at multiple elevations within the tank to detect layering effects. During the charge phase, we confirm the intended inlet and outlet temperatures and watch for the development of the cold layer, ensuring the system is functioning as designed. In the discharge phase, the focus shifts to verifying usable energy output and the stability of the outlet temperature. During standby, it's important to check isolation, heat gain, and confirm there's no unintended mixing that could reduce efficiency. We also test the pump duty and standby modes, bypass functionality, and motorized valve end switches to ensure the entire system operates smoothly. Importantly, we do not rely solely on temperature from the tank volume when assessing TES. Instead, we calculate usable energy by integrating measured flow and temperature over time. Lastly, make sure to confirm actual approved equipment, its ratings, and test boundaries on site, as setups can vary. This thorough approach ensures reliable commissioning and optimal system performance. On this slide, we're focusing on PHE performance, which relies heavily on three key factors: heat balance, approach, and pressure drop. First, it's crucial to understand that achieving a close heat balance alone is not enough if we have excessive pressure drop or the terminal temperature is inadequate. Looking at the hot side duty, we calculate the heat transfer using the density, specific heat, flow rate, and the temperature difference between the inlet and outlet on the hot side. Similarly, for the cold side duty, we use the corresponding values on the cold side, but here the temperature difference is between the outlet and inlet of the cold side. The balance error, which indicates how well the heat transferred on both sides matches, is determined by the absolute difference between hot side and cold side duty divided by their average. Terminal approach refers to the minimum temperature difference at the hot or cold terminal, and this must be carefully monitored. Regarding pressure drop, we measure this at an approved flow rate and compare it against the design or OEM's specified allowance. If the pressure drop is higher than expected, before we consider reducing plate area, we need to investigate possible causes like air in the system, fouling, bypass conditions, sensor mismatches, or even incorrect flow direction. These factors can significantly impact performance and must be ruled out first. On this slide, we focus on the three distinct valve lineups for TES operation: charge, discharge, and standby. It's crucial to always use an approved PNID and position feedback, rather than just relying on the commanded state, to confirm the lineup. During the charge phase, cold supply water enters the approved tank connection, pushing warmer water back in return. In the discharge phase, the tank supplies the critical loop when the plant output is unavailable or limited. Standby mode isolates the tank to prevent unintended circulation, while we continuously trend temperatures. Additionally, there's a bypass to maintain minimum flow and hydraulic continuity when needed. TES pump operation includes duty and standby modes, with flow-proof and restart capabilities. We monitor sensors at 5 or more elevations along with supply, return, flow, and power to ensure accurate TES operating proof, which combines valve feedback, flow, temperature profiles, and usable energy. On this slide, we're focusing on the commissioning of the CDU, which is essential for proving both the facility and technology cooling loops. The The key point here is that the rack interface, coolant chemistry, leak response, AAB power, and controls all fall within the equipment boundary, ensuring comprehensive coverage. Starting with the facility water loop, we need to check isolation, filtration, differential pressure, flow, and the plate heat exchanger approach to confirm everything operates correctly. On the technology cooling loop side, attention is given to fluid quality, pumps, the reservoir, and deaeration to maintain proper cooling performance. The rack manifold and quick connects require proper labeling, torque verification, drip control, and easy access for maintenance. For cold plates or simulated loads, we measure supply and return temperatures along with heat capture to validate cooling efficacy. Leak detection systems must clearly identify zones, trigger alarms, initiate pump and valve responses, and support dry reset functions for safety. It's crucial to verify AAB power setups, controller failover mechanisms, communication loss response, and evidence integration with DCIM or BMS. Remember, a CDU is not just accepted when the pump starts. Instead, we prove stable coolant delivery and controlled responses to leaks, power failures, and communication issues. The illustrative setup on site should always verify that the actual approved equipment, ratings, and test boundaries meet project requirements. On this slide, we focus on the critical role of CDU pre-commissioning in protecting the rack loop from contamination and gas. Cleanliness and fluid compatibility aren't just housekeeping preferences. They are essential reliability requirements. On the mechanical side, we conduct pressure and leak tests using approved media to ensure system integrity. We also thoroughly flush the system, inspect filters, and review particle and cleanliness results. Attention to detail with hoses, manifolds, supports, and maintaining proper bend radius is key to avoiding damage. Isolation, drain, fill, vent, and service clearances must be carefully managed. When it comes to coolant, only approved fluids are used, matched for material compatibility. Parameters like concentration, conductivity or resistivity, and inhibitor levels are carefully checked. Additionally, dissolved gas levels and deaeration are monitored along with reservoir levels. Sampling points are established, and baseline certificates are documented to track system conditions over time. Control systems are equally important, with sensor calibration and point-to-point checks ensuring accurate readings. Pump, variable speed drive, and valve commands and feedback are verified. Local human-machine interfaces, building management systems, or data center infrastructure management systems are integrated and time-synchronized. Finally, alarm settings for leaks, low flow, high temperature, and filter differential pressure are configured to promptly detect issues. All these steps work together to maintain system reliability and prevent contamination that could seriously impact data center operations. On this slide, we're focusing on how the CDU FPT and IST work together to manage heat capture while responding to system faults. First, we apply a representative rack load and let the system reach a steady state. Then, we introduce one approved fault at a time to observe how the system reacts. The expected response includes maintaining the required secondary flow and supply temperature, ensuring a heat balance between the PHE and rack loop, and having standby pumps or controllers step in as needed. It's crucial that the rack inlet coolant stays within the project parameters. As we monitor the system, watch out for issues like air entrainment, pump cavitation, unstable differential pressure control, common power or network dependencies, and any leak alarms that don't trigger the correct isolation response. Key evidence to track includes facility and TCS flow and temperature differentials, pump speed and power, valve states, leak zone events with alarm histories, and rack manifold pressures during recovery. The test is considered successful if there are no uncontrolled leaks, thermal excursions, or cascade failures. All faults alarm correctly, and the system returns to normal lineup. This comprehensive approach ensures reliability and safety in the data center cooling system. On this slide, we're looking at how SPLC state points enable us to test the entire thermal path comprehensively. Each state point provides critical information including a measured value, the current control state, trends over time, and an acceptance note to ensure proper operation. Starting with S1, we monitor the IT heat load in kilowatts, as well as rack inlet, return, and hotspot temperatures. Moving to S2, we focus on the CRAH or FW units, checking supply air, airflow, fan operation, and valve positions. S3 covers the chilled water supply, capturing temperature, flow rates, differential pressure, and pump status. Then at S4, we observe the chilled water return temperature and calculate the temperature differential. S5 gives us insight into the plant's performance, including chiller loading, staging, power consumption, and alarm conditions. Finally, S6 looks at the rejection side, measuring ambient conditions, approach temperatures, fan and pump activity, and recovery status. The key here is the state point acceptance criteria, which combines measured values, control actions, trends, and margins to ensure system reliability and efficiency. When dealing with liquid cooling fluid and leak tests, it's crucial to understand that project-specific criteria must guide every step. Different facilities use distinct water types and cooling fluids depending on their technology, and each requires unique sampling protocols, compatible materials, and tailored incident responses. We start by ensuring fluid quality, which includes verifying approved chemistry and concentration levels, and measuring conductivity or resistivity where applicable. It's also essential to monitor for particles, corrosion products, and microbial contamination to maintain system integrity. Compatibility between materials and seals plays a significant role in preventing leaks. Leak detection involves strategically placing cables or probes according to a defined zone map and conducting controlled wet simulations, or employing approved test methods. Alarms should be integrated locally and linked to the building management system or data center infrastructure management to provide timely alerts. Pumps and valves must respond only as designed to prevent further issues. In the event of a leak, recovering the system means containing and isolating the smallest practical segment, protecting electronics, and thoroughly removing any residual fluid. Inspecting quick connects, hoses, and affected devices is essential before performing a dry reset. Finally, proving the system is leak-free and officially closing the issue ensures long-term reliability. On this slide, we focus on how MAU, ventilation, and room pressurization work together to protect the environmental boundary in a data center. One key point is to commission normal ventilation functions separately from smoke control mode and external contamination isolation, ensuring each system operates effectively on its own. During normal operation, we carefully monitor outdoor and return air paths along with filters to maintain air quality. We also control airflow, temperature, humidity, and dew point to create the ideal environment. Maintaining proper room pressure and ensuring door operation supports containment is crucial. If the system includes economizer or free cooling features, we check their permissives to maximize efficiency. In case of failure or isolation events, it's important to verify fan loss responses and standby operations, damper fail positions, and the ability to shut off contaminated external air. We also prepare for sensor or network loss by having local fallback controls in place. Evidence of proper system functioning includes airflow traverses and pressure mapping, monitoring filtered differential pressure and fan power, and tracking BMS commands, feedback, and alarms. Finally, observing door and containment leakage gives us practical insight to verify environmental integrity. On this slide, we're focusing on the critical need for generator support cooling to function effectively during the electrical conditions that generate heat. The main heat sources include the engine jacket and charge air heat, alternator and exhaust radiation, as well as losses from the fuel system and auxiliary components. It's important to remember that when multiple generators run at the same time, the cooling demands increase significantly. During testing, we simulate generator load steps and sustained holds while closely monitoring room intake and exhaust airflow, pressure, coolant temperatures, fan and pump operations, and the ambient environment. We also check the system's response to the loss of a fan, cooling cell, or controller. The goal is to ensure that OEM temperature limits are never exceeded, that hot discharge air doesn't short-circuit back into the room, and that standby capacity and alarm systems function correctly. Finally, the cooling system must demonstrate safe restoration once utility power returns. All these steps ensure reliable cooling performance under the most demanding electrical scenarios. On this slide, we're focusing on the commissioning of water treatment auxiliaries as active control systems. It's essential not only to verify that motors are rotating, but to prove the actual process results and alarm functionalities. Sidestream filtration, for example, must be tested for design flow, differential pressure, backwash or cleaning routines, and bypass operation. We monitor flow and pressure trends, filter condition, and waste pathways to ensure everything functions as designed. For chemical dosing, calibration of pumps, tank levels, interlocks, and containment are tested alongside dose rate calculations and alarm verifications to maintain proper chemical baselines. Conductivity blowdown involves sensor calibration, setting appropriate set points, valve functionality, and interaction with makeup water, with ongoing trend tracking of conductivity, blowdown volume, and valve feedback. The ball cleaning system commissioning checks ball counts, injection and recovery cycles, strainers, alarm systems, recovery rates, pressure drops, and tube cleaning sequences. Lastly, the makeup system's metering, low pressure and quality alarms, and isolation functions are verified, supported by volume balance and water quality records. Together, these tests provide comprehensive acceptance evidence that each subsystem performs reliably and safely within the overall water treatment process. Now we're entering Section 03, where we'll dive into controls, instrumentation, and data platforms. Here, we'll explore crucial aspects like point-to-point proof and redundant control, which ensure system reliability. We'll also discuss tuning techniques, the role of alarms and trends in monitoring, and how all of this contributes to trusted operational evidence that supports decision-making and safety. Understanding these elements is key to optimizing performance and maintaining control integrity. With this foundation, we can build more robust and dependable systems. Point-to-point testing means verifying the entire signal path from start to finish, ensuring that every step works correctly. First, we create a physical event at the source. Then we verify the input for proper range, units, scaling, and data quality. Next, we check the logic to confirm permissives, commands, and safety boundaries are accurate. After that, we verify the output by checking actuator or device feedback. We also confirm the platform displays the correct graphics, alarms, trends, and timestamps. Finally, we test the operator's ability to acknowledge and execute the standard operating procedure. This comprehensive approach guarantees the system's reliability and performance. On this slide, we're focusing on the importance of a redundant PLC and OT architecture that can fail over seamlessly without losing control. This means during testing, we need to consider every critical aspect, from controller power and I/O to network paths, servers, historians, and local fallback boundaries. Each component must have dual roles and continuous health monitoring to ensure reliability. Power supplies should be independently backed up through UPS systems, and networks should have multiple paths with managed failure behavior to prevent outages. Additionally, firmware and configuration control are vital to maintain system integrity. Even if optimization processes fail, the local equipment controller must continue to operate safely, ensuring cooling safety and stable local control at all times. Lastly, alarms from BMS, CPOS, and DCM systems help differentiate between a loss of system optimization and an actual loss of control, which is crucial for rapid troubleshooting. Remember, the setup shown here is for illustration. Always verify approved equipment, ratings, and test boundaries on site to match your actual system. On this slide, we're focusing on how control's resilience is thoroughly tested by domain, rather than through indiscriminate power removal. The approach is to inject one controlled fault at a time, then carefully observe the automatic system response, followed by restoring the system and verifying synchronization. Looking closely at each domain. For controllers, we test active and standby modes, warm start capabilities, and bumpless transfer to ensure smooth transitions. For I/O, we simulate remote rack loss, check for bad quality signals, and confirm the system enters a safe state when needed. On the network side, we introduce ring breaks, switch losses, and verify path convergence to maintain communication integrity. For servers, we focus on application failover and maintaining historian continuity, which are critical for data reliability. Power tests involve A, B, and DC source losses along with the system's ability to ride through these disruptions. Additionally, local fallback is tested through hard-coded limits and manual or local operation modes. Finally, the control service is evaluated to guarantee safe plant operation, observability, and recoverable configuration, ensuring the system remains robust and reliable even under fault conditions. On this slide, we're focusing on the critical role of sensor validation, which is all about distinguishing between instrument error and actual process behavior. The key is to compare the installed sensor with a calibrated reference right at the actual operating point to ensure accuracy. Starting with the physical aspects, it's crucial that the sensor is installed in the correct location with proper immersion and orientation. This ensures it represents the process accurately without being affected by heat conduction or poor mixing. We also need to consider the sensor's range, response time, environmental ratings, as well as tagging and ease of access for maintenance. Next, we look at the signal side. We validate the raw input, engineering units, and any scaling applied. It's important to check how the sensor behaves when there's an open circuit, short circuit, or out-of-range condition. Filtering of the signal and how bad quality data is handled to avoid propagation errors is also validated. Additionally, the controller's fallback or voting logic plays a role in managing signal reliability. Finally, the platform layer involves confirming that the sensor data is correctly represented graphically with appropriate units. We verify trend intervals and data retention to ensure good historical analysis. Alarm thresholds, delays, and hysteresis are tested to respond correctly to changes. And last, timestamps and operator guidance are essential for clear interpretation and timely action. Together, these steps ensure the sensor's reliability, so that we can trust the data for optimal process control. On this slide, we focus on actuator testing, which is essential to verify that valves or dampers not only receive commands, but actually move to the correct hydraulic or airflow state. Command alone is not enough evidence of proper operation. We start by looking at various devices and the specific functional and failure checks required. For PICV and PICCV, we test the valve at different command positions, 0, 25, 50, 75, and 100%, to observe flow response, differential pressure range, and shutoff performance. We also check for power or communication loss, manual override functions, and ensure end-state alarms are working. For isolation valves, important checks include open and close times, torque levels, limit switch operations, and verifying there is no leakage, ensuring proper isolation. Potential failures like stuck valves or mismatches between local and remote control positions are also inspected. Control dampers require checking blade direction and linkage, stroke length and pressure or airflow response. Testing includes simulating power loss, verifying fire mode functionality, and identifying any feedback discrepancies. Smoke dampers must confirm the approved fire command activates correctly, along with end switches and access for manual reset. Fault annunciation, emergency power availability, and manual override are also crucial verification points. Finally, for VSD-driven fans or pumps, testing ensures speed reference and feedback are accurate, respecting minimum and maximum limits. We evaluate ramp times, interlocks, and check for faults or bypass features if designed. Motor protection and proper restart sequences complete the validation. Together, these tests confirm that actuators perform reliably and safely under all operational conditions. On this slide, we're focusing on PID step response testing, which is crucial for assessing system stability rather than just looking for smoothness in the response. When conducting these tests, it's important to apply a safe and approved step input, then carefully evaluate the system's overshoot, settling time, steady-state error, and how it interacts with equipment staging. Interpreting the resulting plot helps us understand system behavior. Keep in mind that acceptance bands for performance are specific to each project, so they can vary. Also, be sure to check parameters like minimum speed, valve authority, and any staging interactions to confirm they operate correctly. Most importantly, watch for any signs of sustained hunting or the system hitting safety limits, as these indicate instability and potential issues that need to be addressed. This approach ensures the MVAC system's performance is both stable and reliable. On this slide, we focus on the essential elements required for effective alarm acceptance in a data center MVAC system. An alarm list without clear operational intent can lead to alarm floods and create unsafe ambiguity. To prevent this, each alarm must be thoroughly defined with specific conditions like the exact variable or state and its threshold. The stimulus that triggers the alarm must reliably reach the controller and platform to ensure accurate detection. We also need to consider delay or hysteresis settings to avoid nuisance alarms while still detecting rapid hazards promptly. This timing is measured from the onset of the condition to its clearance. Priority and routing are crucial too, ensuring the right operator receives the message and escalation occurs appropriately, with alarms arriving at the correct workstation and notifications. Automatic responses should be designed as safe sequences that respect local protection boundaries, including commands and feedback leading to the resulting process state. Operator actions must be supported with clear SOP references for first response, along with acknowledgement procedures and action drills. Finally, reset conditions must be well defined, whether automatic or manual, ensuring no alarms remain latched or hidden. This comprehensive approach helps maintain safety and clarity in alarm management. On this slide, we're focusing on how historian and trend commissioning plays a critical role in preserving the evidence chain during system testing. First, it's essential that trends are set up properly before test week begins, and after each test scenario, data needs to be exported in its raw form to maintain accuracy. When configuring the historian, pay close attention to point names, units, and quality flags to ensure consistency. The sampling interval should match the speed of the events being monitored, and any deadband or compression settings must be thoroughly documented. Synchronizing time using NTP or PTP sources and the correct time zone is key to avoiding discrepancies. Continuity is another crucial aspect. We need to handle network interruptions with store and forward methods, ensure server failover capabilities, and confirm the historian restarts without losing data. Avoiding duplicate or reordered timestamps guarantees data integrity. Finally, retention policies and access controls safeguard the historical data. Throughout the process, protect the raw data files from being overwritten, record software and configuration versions meticulously, and create index links that connect plots, screenshots, and manual sheets to build a comprehensive, reliable evidence chain. On this slide, we focus on the critical distinction between water leak and fuel leak tests as separate risk controls. These two types of leaks pose very different hazards, so they require different sensors, automatic responses, and testing methods. For water leaks, detection typically happens in data halls, CRAH or CDU units, chilled water systems, condensate, and other wet services. The sensors used can include sensing cables, probes, drain pans, or zone modules, and the tests involve controlled water contact followed by a dry reset. In contrast, fuel leak detection is critical around bulk and day tanks, transfer pipes, pumps, polishing units, and generator rooms. Here, the sensors are specialized hydrocarbon cables or probes, interstitial sensors, or sump sensors, and testing must use approved safe simulation methods without any uncontrolled release. The automatic responses also differ. Water leaks trigger alarms and optionally valve or pump actions, while fuel leaks cause alarms coupled with pump inhibit or shutdown and environmental responses. Finally, the evidence collected varies. Water leaks produce zone maps, screen captures, and dry-proof resets, whereas fuel leaks require leak maps, interlock chronologies, and incident procedure documentation. This clear separation ensures that both risks are managed effectively and safely. Here we focus on the critical aspects of fire, smoke, and emergency ventilation interfaces. The key point here is to demonstrate the complete chain of events, starting from the approved fire trigger all the way through to the fan activation, damper control, pressure monitoring, and ultimately ensuring a safe reset of the system. This overview is essential because it shows how each component interacts seamlessly to maintain safety during emergencies. Smoke control commissioning is all about ensuring that every part of the system works together seamlessly to keep people safe during an emergency. This includes verifying fans, ducts, dampers, controls, emergency power, fire alarms, and the building management system as one complete test boundary. We follow the project-approved cause and effect matrix to guide our testing, confirming fan rotation, airflow paths, damper positions, and end switches are all functioning correctly. We also measure pressure differentials and how door openings affect airflow to ensure proper containment. It's crucial to verify that duty and standby systems switch correctly, emergency power kicks in when needed, and fault alarms operate as expected. We capture timestamps from fire alarm and building management systems to check manual overrides and resets, while making sure motor protections and safety interlocks remain effective throughout. Remember, any simulated smoke tests must be done safely without creating uncontrolled life safety hazards, and it's essential to verify that all equipment and test boundaries on site match the approved specifications. This slide covers the smoke extract test, which is crucial for proving zone clearance and replacement air control in the data center MVAC system. To trigger the test, we initiate the approved fire zone signal and run the smoke control sequence. The expected response includes the correct extract fans and dampers starting or moving, the makeup air path opening as designed, and adjacent protected zones maintaining their intended pressure relationships. Additionally, the fire panel and BMS or FAS must display the correct feedback. During the test, we need to watch out for potential issues like short circuits between makeup and extract air, door force or pressure values that fall outside approved limits, incorrect damper or fire zone mappings, and any uncontrolled fan restarts or bypassing of protection systems. Evidence collected to verify the test includes airflow and pressure readings, damper end switch matrix data, fan and VFD status and power levels, as well as event logs, video footage, and reset records. Acceptance is achieved when all measured airflow, pressure, and system responses fully meet the approved fire engineering design and authority having jurisdiction criteria. This ensures the smoke control system operates safely and effectively during a fire event. On this slide, we focus on pressurization tests, which are crucial for ensuring safety and proper function in data center MVAC systems. Pressurization tests cover doors, relief paths, and potential failure modes, with required pressure values that vary depending on the project and relevant codes. We always measure pressure across the intended boundary in different door conditions. Starting with all doors closed, we check that stair, lobby, and shaft pressure differentials are within approved minimum and maximum limits, making sure relief paths remain stable. When one representative door is open, we observe residual airflow and fan response, ensuring that tenability is maintained without creating excessive door force. In scenarios where multiple doors are open, like firefighting mode, we verify pressure distribution by level to prevent any adverse flow reversal or uncontrolled overpressure. We also test for duty fan failure, confirming that the standby fan starts automatically, pressure recovers correctly, alarms trigger as expected, and there's no unsafe pressure dip. Finally, if there's a power or control fault, it's vital that emergency supplies, local or firefighter overrides, and system feedback function properly, so the approved fire mode remains available at all times. These tests ensure system reliability and occupant safety under various conditions. On this slide, we're focusing on the crucial relationship between door testing and pressure differentials. Door testing reconciles pressure with opening force to ensure both safety and functionality. A high pressure difference can help improve smoke resistance, which is essential for fire safety, but it can also make it difficult for people to exit or for firefighters to gain access. To properly test this, we measure the pressure differential using a calibrated low-range manometer across the specific door boundary. At the same time, we measure the opening force right at the approved handle location, taking into account the direction the door opens. It's important to also record the test conditions carefully. This includes noting the door closer, seals, the latch status, any adjacent doors, as well as fan modes and environmental factors like wind or stack effects. The final decision depends on ensuring that both the pressure differential and the opening force meet the criteria set out in the approved fire strategy and relevant codes. Remember, there is no one-size-fits-all pressure value. You must always consult the adopted code, the fire engineering report, and the authority having jurisdiction's interpretation to get it right. This slide covers the important steps for post-agent purge testing, which must be controlled by the approved clean agent design. First, before starting, we confirm the discharge, abort, and hold logic along with impairment controls. We also define safe simulated triggers and occupancy restrictions. It's crucial to verify the purge fan, dampers, and the discharge path, while protecting detectors and environmental monitoring systems. During execution, we initiate the approved post-discharge or purge sequence, verifying the sealing and opening order, as well as fan proof. We then measure clearance using approved methods and confirm there's no migration to unintended zones. Finally, during restoration, we reset the releasing and fire panels, return the room to normal pressure and ventilation, clear alarms and temporary overrides, and document the agent-specific procedures along with operator training to ensure safety and compliance. This slide highlights the cause and effect matrix, which serves as the integrated fire test script for the data center MVAC system. The matrix is designed to test every critical function systematically, using project-approved inputs and verifying expected outputs with accurate timestamps and restoration procedures. For example, when a data hall smoke alarm triggers, the system ensures the CRAH, MAU, and dampers respond correctly, without causing unintended cooling loss. Meanwhile, this event is recorded through the fire alarm system and building management system, providing device feedback and room status. Similarly, commands like smoke extraction activate the proper sequences for extract, makeup, and pressurization, with continuous monitoring of fan and damper statuses, airflow, and emergency power. The pre-discharge of clean agents is carefully checked to confirm that HVAC components, doors, and dampers operate as designed, including countdowns, abort or hold functions, alarms, and resets. Fault scenarios such as fire panel faults are handled to prevent unsafe plant actions, generating alarms and operator alerts while maintaining monitoring integrity. Finally, emergency power events are tested to ensure life safety ventilation remains available, tracking transfer chronology, fan restarts, and pressure recovery. This comprehensive matrix ensures that every element works together seamlessly to protect the data center environment during fire events. Here, we are focusing on heat load testing. This process involves a carefully measured thermal experiment designed to evaluate several critical factors: the system's capacity to handle heat, its spatial stability under thermal stress, the redundancy built in to prevent failure, and its ability to recover after heat exposure. Understanding these elements is essential for ensuring reliable performance in real-world conditions. HLT begins with a safe, representative, and observable load arrangement, which is crucial for accurate testing. Temporary heat must closely mimic the intended spatial and electrical loading without causing recirculation or posing any cable risk. We carefully select the load bank type, its kW rating, and ensure proper calibration and verification. Placement of racks or zones follows a heat density map to maintain realistic conditions. Attention to circuit source, cable routing, protection, and emergency stops is essential for safety and reliability. The air discharge path must prevent any self-recirculation of heat to ensure accurate results. Sensors are placed strategically at rack inlets, return air points, and critical room locations to monitor conditions precisely. We also enable trends for chilled water, airside parameters, plant power, and control systems to track performance thoroughly. Remember, HLT is not just a cosmetic demonstration, but a controlled experiment with clearly defined variables and uncertainties. Finally, an illustrative setup on-site must be verified to confirm the actual approved equipment, ratings, and test boundaries before proceeding. On this slide, we focus on the importance of choosing load banks that align with both the thermal conditions and the system boundaries for effective commissioning. Electrical and thermal implications must be commissioned together to ensure accurate and reliable system performance. We begin with rack-resistive heaters, which are ideal for proving spatial rack and aisle airflow, as well as containment effectiveness. Key controls here include monitoring air discharge, fan characteristics, rack distribution, and cable routing. Next, portable air-cooled banks are best used to simulate heat in a room or plant area. It's critical to manage hot air recirculation, noise levels, and establish clear exclusion zones along with sufficient ventilation. Water-cooled load banks are suited for high electrical loads without relying on room air heat rejection. When using these, we must closely monitor hydraulic capacity, have interlocks for low flow and high temperature conditions, and prepare for proper cleanup. Server or synthetic IT loads offer the most representative electrical and airflow behavior, closely mimicking real-world IT environments. This requires managing IT risk effectively, controlling workload, and leveraging telemetry for timely rollback if necessary. Lastly, process or load simulators focus on CDU or liquid cooling loop performance. They demand attention to coolant compatibility, flow proving, and prompt leak response mechanisms. Each type of load bank plays a specific role, and ensuring their proper use with the right controls is essential to a successful commissioning process. This slide focuses on the temporary power plan during commissioning, which functions as a system on its own. Before applying full heat, it's crucial that the load bank connection, cable protection, and emergency shutdown are thoroughly accepted and verified. Starting with capacity and protection, we need to consider the source and distribution capacity, make sure breaker and fuse settings are properly coordinated for selectivity, and carefully evaluate cable ampacity, derating, and voltage drop. Proper earthing and bonding, along with correct connection ratings, are fundamental to safety. On the physical side, segregated cable routes and mechanical protection prevent damage, while inspection of camlock terminations and ensuring correct torque are essential checks. Thermal scanning at each load plateau helps identify hotspots early. Safety barriers, clear signage, and fire extinguishing provisions must also be in place. For operation, remote and local emergency stops provide quick shutdown capability. Load step control with fail-safe removal mechanisms prevents system overload. Additionally, fan and flow interlocks ensure heaters operate only under safe conditions. Finally, damage-free disconnection and careful reinstatement allow maintenance without risking system integrity. These elements together create a robust temporary power plan critical for successful commissioning. The key to effective thermal management in data centers is that the thermal sensor grid must reveal local hot spots, not just average them away. To do this, we need to carefully map instruments to specific points like rack faces, aisles, containment boundaries, and plant measurements, all using a consistent coordinate system. For rack inlets, sensors should capture temperatures at the bottom, middle, and top of representative racks to get a detailed profile. Similarly, monitoring rack return air helps us understand hot aisle distribution and potential recirculation issues. In the room environment, it's important to track high and low levels, the perimeter, and any known risk zones where temperatures might vary. On the air side, we measure supply and return conditions from CRAH or FW units, along with pressure, to ensure airflow is properly balanced. Waterside measurements include flow rates, chilled water supply and return temperatures, differential pressure, and valve states to verify cooling efficiency. Electrical monitoring tracks actual kilowatt loads by zone and total load, linking thermal data with power consumption. Finally, this data comes together in a time-synchronized thermal map that includes location ID, height, sensor ID, and uncertainty, providing a comprehensive and actionable view of the thermal environment. This detailed mapping is critical for precise diagnostics and optimized cooling strategies. On this slide, we focus on the critical stages of the commissioning process for the data center MVAC system. First, you need to interpret the plot carefully to understand system behavior. Before moving forward, always declare your stability criteria to ensure consistent and reliable results. Then, hold the system at full load for the approved soak period as specified in the test script. It's important to execute only one failure at a time to isolate issues effectively. Finally, return the system to normal operation and prove there is no residual state lingering from any disturbances. Remember, the exact percentages and durations you use will depend on the approved test script and the temporary power available. On this slide, we focus on the concept that each HLT plateau closes a specific question. It's important to understand that we don't move forward just because time has passed. Instead, we advance only when the required condition is stable and all the necessary evidence is complete. Starting with the baseline, we check the initial state, ambient conditions, and alarms. At 25%, we verify sensor plausibility and the first response. Moving on to 50%, we look at control margin and distribution. By 75%, we focus on staging and identifying any emerging hot spots. At 100%, we confirm design capacity and full load power. The soak phase ensures thermal and control stability. Then, during failure, we assess the rate of rise and recovery. Finally, at restore, we check as left readiness to ensure everything is set for normal operation. This step-by-step approach ensures thorough testing and reliable system performance. In this slide, we focus on the HLT heat balance test, which checks whether the measured load actually reaches the cooling medium. It's important to first account for auxiliary heat sources, heat stored in the room, and any unmeasured boundary losses before we consider any discrepancies. We start with the applied electrical heat, represented as the sum of the measured load bank kilowatts. Then, on the water side, heat capture is calculated using the flow rate, specific heat capacity, and temperature difference. Similarly, the airside check involves air density, specific heat, air volume flow, and temperature difference. The key term here is the residual heat, which is the difference between the total input heat, auxiliary heat, waterside heat, stored heat change, and losses. This residual helps us diagnose the system's performance. Crucially, we must avoid forcing the heat balance to close by arbitrarily adjusting sensor readings that haven't been verified. This approach ensures accuracy and reliability in our analysis. Thermal stability is all about ensuring every critical point in the system stays controlled within set limits. To understand this better, we plot the maximum rack inlet temperatures, percentile distributions, chilled water supply and return temperatures, along with control outputs all together. Interpreting this plot accurately is key. We need to use project-specific warning and critical limits to know when something is out of range. Also, it's important to review the spread and rate of temperature rise rather than just focusing on averages. By doing this, we can clearly see how fan speeds, valve positions, and chiller actions correlate with temperature changes, helping us maintain optimal thermal stability throughout the data center. On this slide, we're looking at the concept of capacity margin and how it separates test duty from redundancy. It's important to understand that the design margin, future growth, and standby capacity are distinct quantities and should never be counted twice. Starting with measured available duty, this refers to the capacity available under declared ambient conditions and the specific lineup of equipment. Test duty, on the other hand, comes from the calibrated load and heat balance during testing. The operating margin, represented as M, is the difference between the available capacity and the test duty, essentially showing the buffer you have in normal operation. Next is the failure state margin, or MF, which looks at capacity available after a scripted outage minus the protected load, highlighting your resilience during faults or maintenance. It's critical to remember that future growth represents a separate demand scenario and is not a form of redundancy. Finally, passing a normal N+1 configuration test doesn't necessarily prove that your system is concurrently maintainable or fault-tolerant. This distinction is key for ensuring true reliability in your MVAC system. In this slide, we focus on containment breach testing, which is critical for verifying how the system handles redistribution and recovery. The test is triggered by opening or removing one approved containment panel or door while operating at a stable, representative load. We expect to see pressure and airflow redistribute correctly, with fan and valve controls responding smoothly and without instability. It's important that rack inlet temperatures stay within the approved transient limits throughout this process. Additionally, alarms and operator guidance should function accurately where they are designed to do so. During testing, we need to watch out for potential issues such as unsafe loose panels or unauthorized access. We should also be aware that sensor grids might be too sparse to detect local recirculation accurately. Another concern is that control responses might unintentionally starve airflow in another zone, and we must avoid any unapproved prolonged exposure. The evidence for a successful test includes monitoring aisle pressure, the rack inlet temperature grid, fan and valve commands, thermal imaging, and the recovery time. Ultimately, we will accept the test if there is no uncontrolled thermal runaway and the containment boundary is restored, confirming that the system has returned to its original stable condition. This ensures the data center's MVAC system remains reliable and resilient under breach scenarios. When closing the HLT, it's crucial to understand that removing heat is not the same as fully restoring the plant, controls, and room to their approved normal state. The process involves several careful steps. First, we unload by stepping down without destabilizing the plant. Next, we cool down while observing recovery and maintaining minimum load control. Then, we remove any temporary works, ensuring safe isolation and checking for damage. After that, we restore controls such as set points, schedules, and overrides. It's important to verify that there are no residual, inhibited, or stale alarms left. We also back up evidence through raw files and screenshots for accountability. Finally, we conduct a debrief to discuss any issues, plan retests, and capture lessons learned. Each step ensures a controlled and safe restoration of the system. This section focuses on integrated systems testing and resilience. The key idea here is managing one controlled disturbance at a time. This involves an automatic response to disturbances, ensuring the protection of critical loads, gathering evidence during events, and conducting deliberate restoration afterward. Each step is designed to enhance the overall resilience of the system. Here we see how the IST method is designed to protect both the service and the integrity of evidence during testing. The key idea is that the trigger itself is just one step in a comprehensive process. This process includes establishing a stable baseline first, ensuring everything from topology to alarms are well understood. Then, after confirming authority and safety in the pre-brief, a single approved trigger event initiates the test. We then observe the system, allowing it to respond automatically as designed, followed by holding the response for a defined duration to gather data. After that, we restore the system to an approved normal state. Finally, a decision is made to pass or fail the test, and if necessary, identify issues and schedule retesting. This structured method ensures a thorough and safe validation of system performance. On this slide, we're looking at how event chronology helps us distinguish between fast protection actions and slower thermal responses in a data center MVAC system. The key is to use a high-resolution electrical record alongside slower thermal trend data, both aligned on the same time base. It starts at T0, the initiating event, which triggers a series of protective actions within milliseconds. This includes protection mechanisms and static transfer switches activating quickly. Then after a few seconds, equipment like generators, automatic transfer switches, PLCs, and standby systems come online to support the transition. Over the course of minutes, you'll see thermal responses such as chilled water system temperature and room temperature start to shift, reflecting the physical changes in the environment. The system then moves into a stabilization phase, reaching a new steady state that meets the set criteria. Finally, restoration happens when normal system topology is re-established and all alarms are cleared, signifying a return to standard operation. This timeline clearly separates the immediate protective measures from the gradual thermal changes, helping us understand and manage the system's response effectively. In this slide, we focus on the utility loss integrated systems test, which is designed to prove cooling ride-through capability and confirm the restart sequence. The test is triggered by removing the approved utility source while the system is under representative electrical and thermal load. During this, the UPS and control power must maintain critical controls and telemetry without interruption. Generators are then expected to start and transfer power sources in the approved sequence, ensuring a smooth transition without any power loss. Meanwhile, the thermal energy storage, buffer tanks, or system thermal inertia work to protect the load during the restart process. Pumps, fans, and chillers must restart without causing overloads or cascading failures that could compromise system stability. We need to watch carefully for any PLC or network reboots that create blind spots in telemetry, simultaneous motor restarts that might overload generators, loss of pump flow before chillers come back online, and any return to utility instability or automatic transfers that go against the sequence of operations. To verify everything ran correctly, we review power quality monitoring and energy management system waveforms, generator and automatic transfer switch chronologies, plant equipment restart timelines, as well as chilled water supply and rack inlet temperature trends. Ultimately, the test is accepted if there are no unacceptable critical load or thermal excursions, and all alarms and restorations align perfectly with the approved sequence of operations. On this slide, we're focusing on the chiller trip IST tests, which evaluate the staging logic and residual capacity of the system. The test is triggered by tripping or inhibiting one operating chiller using a safe, approved method. The expected response is that the failure is detected with the correct alarm, and the standby chiller kicks in after the necessary permissives and timers. Pumps and valves should then establish the correct flow, and both chilled water supply and protected temperatures must recover within the defined criteria. Keep an eye out for issues like the anti-recycle timer blocking the required response, any shared condenser or chilled water components causing a common mode failure, control hunting during overlap, and potential capacity shortfalls under current ambient conditions. Evidence to monitor includes chiller states and alarms, flow and differential pressure readings, valve positions, the chilled water supply and return trends, as well as load and recovery time. The test is accepted only if the required protected duty is maintained without cascade and normal rotation is deliberately restored. On this slide, we focus on the pump trip IST test, which is designed to verify hydraulic continuity in the system. The test is triggered by tripping one duty chilled water, condenser water, or tower cooling system pump while operating at a stable load. The expected response includes detecting a flow loss without causing unsafe chiller operation, the standby pump starting automatically, and check valves preventing any reverse flow. Additionally, differential pressure control should stabilize smoothly without overshoot, and terminal units or cooling distribution units must maintain the required flow. During the test, it's important to watch for potential issues like deadhead conditions or minimum flow violations, non-return valve slams or surges, dependency on a common variable speed drive or control power, and sensor placements that might hide remote flow shortfalls. We gather evidence from pump command and feedback signals, flow readings, differential pressure data, chiller or CDU interlocks, and surge or pressure recovery trends. Finally, the test is accepted when no damaging hydraulic transients occur and the most demanding load stays within its approved operating limits. This slide focuses on the CRAH and FWU loss integrated system test, specifically within the protected zone. The test begins by disabling one unit or fan module within the approved test zone as a trigger. We expect the group control system to detect this loss and the remaining fans and units to redistribute airflow efficiently. Meanwhile, chilled water valves and the plant must respond smoothly without oscillation, ensuring that any hot spots recover within the approved time frame. It's important to watch out for potential issues like backflow through the failed fan, temperature averaging that might mask local failures, common mode power or network failures, and replacement modes that may expose personnel to moving parts. We gather evidence through monitoring rack grid and aisle pressure, fan and valve responses, alarms at both the unit and group levels, and the rate of temperature rise and recovery. Ultimately, the test is considered acceptable if the zone remains within the project's thermal criteria and the failed asset can be safely isolated or restored. On this slide, we're focusing on heat rejection loss and how the integrated system test, or IST, helps us understand weather and common mode dependencies. The key trigger here is removing one tower, dry cooler cell, fan, or spray pump function while maintaining a stable load. When this happens, we expect the system to detect the cell failure, and the remaining cells should stage up to the available capacity to compensate. Importantly, the condenser and primary water temperature rise should stay controlled, and the chiller loading should adjust smoothly without causing any cascade of issues. However, we need to watch out for specific factors like shared basins, headers, and control power, as well as potential air recirculation among cells. It's also critical that the water loss mode is configured properly, and we take note if the approach is measured using a biased ambient sensor. To confirm the system's performance, we look at evidence such as ambient and approach temperatures, the operational state of cell fans and pumps, chiller pressures and loading, and the timeline for alarms and recovery. Ultimately, the goal is to ensure protected cooling duty remains available under declared conditions, or that the approved controlled load action takes place effectively. On this slide, we focus on the valve failure IST, which is a crucial test that verifies our feedback, bypass, and isolation strategies. The test is triggered by simulating a control or isolation valve failure, either open or closed, without causing hydraulic shock. The key expected response is that the system detects a command and feedback mismatch, triggering alarms. Then, the control system should automatically select a safe fallback operation, with any bypass or alternate flow path activating only as designed. It's important to be alert during the test for issues like fast valve closures outside of surge study parameters, hidden manual bypasses that might affect the results, control instability due to valve authority, and whether the valve fail position aligns with fire, freeze, or leak risks. Evidence to monitor includes valve commands, end switches, flow, differential pressure, transient pressure changes, temperature outcomes, and operator actions, or how the lineup is left after the test. Finally, acceptance of the test hinges on no damaging surge events, no uncontrolled flow loss, and absence of latent misalignment. The test must strictly follow the approved surge and risk assessment methods to ensure safety and system integrity. On this slide, we focus on the sensor bias IST, which serves to prove plausibility and validate fallback logic in our system. The key point is to trigger the system by injecting an approved biased, frozen, or bad quality value at a critical sensor input. The controller must then detect this implausible or bad quality condition. Following detection, the system should automatically select voting, reference, or local fallback as designed, and an alarm should clearly identify the failed measurement. It's essential to watch for scenarios where optimization attempts might drive equipment based on corrupted values, or where multiple systems share the same unprotected sensor, which can increase risk. Additionally, be aware if the platform displays the corrupted value as valid or if manual overrides become permanent, undermining system safety. Evidence of the system's proper response includes the injected value and reference, visible quality flags and alarms, the control output, and the final process result. Also critical is the system's ability to recover promptly once the original signal is restored. The ultimate goal is clear. The corrupted input cannot cause any unsafe or cascading response, ensuring that normal control resumes without any hidden offset or lasting error. This confirms that our safety and fallback mechanisms work effectively under challenging conditions. On this slide, we focus on the PLC failover integrated system test, or IST, which helps us distinguish between a bumpless transfer and a frozen plant. The test is triggered by deliberately failing the active supervisory controller or server, following the approved redundancy method. What we expect during this failover is that the standby controller takes over the defined role seamlessly. Importantly, critical outputs should remain stable or transition according to an approved fallback plan. Local equipment safeties and controllers must continue to have authority, ensuring the system's safety and reliability throughout the process. Additionally, operators should receive a clear and unmistakable redundancy alarm to keep them informed. We need to watch out for a few potential issues. Having dual controllers powered by the same supply can cause problems, as can unsynchronized configuration or stale state data leading to improper operation. Output bumps might trigger unwanted staging or valve transients, and gaps in the historian data could obscure the event, making troubleshooting harder. To verify the failover was successful, we look for evidence such as the rolls and heartbeats of controllers, output and feedback trends, relevant plant variables, and thorough review of alarms, events, and configuration logs. Finally, if the control service and system observability remain within the approved resilience objectives, and the configuration resynchronizes properly after restoration, we can accept the test as successful. This ensures that the system maintains reliability and safety even during failover scenarios. On this slide, we focus on the OT network failover IST, which is critical to proving communication resilience without losing local control. The trigger for this test involves opening one approved network path or removing a switch or node to simulate a failure. The expected response is that the redundant path converges as designed, ensuring controllers retain their local control without interruption. We want to see points restore with correct quality and timestamps, and platforms should alarm the network fault without causing an alarm storm. It's important to watch out for issues like layer 2 loops or unstable convergence. Any single points of failure such as shared uplinks, firewalls, or gateways, loss of time synchronization, and whether commands replay correctly after reconnection. Evidence to verify success includes switch and network logs, point quality and latency data, BMS or CPOS and DCM continuity, and the alarm and recovery chronology. The test is accepted when there's no loss of the protected cooling function, communication recovery is complete, and no stale or duplicate control actions remain. This ensures our system maintains reliability and control even in network failover scenarios. On this slide, we're focusing on the TES ride-through integrated system test, or IST, which is designed to prove usable time rather than just nominal volume. The key trigger here is to remove or delay active cooling while still maintaining the protected load on the TES and buffer support. During the test, we expect to see a correct discharge lineup and for the pumps to start as planned. It's critical that the supply temperature remains within the project limits, and the temperature profile should move through the tank exactly as expected. The plant restart and transition back to normal operation must also be stable. There are several things to watch out for. Tank mixing or incorrect connections can cause issues. Starting the test with an unverified state of charge can impact results, and bypass short circuits or flow and temperature mismatches can reduce available energy. We gather evidence by monitoring tank elevation temperatures, flow rates, supply and return temperatures, calculated discharged energy, and the timeline for restart and restoration. The test is considered acceptable if the measured usable energy and duration cover the approved interruption scenario with some margin, ensuring reliable performance under these conditions. On this slide, we're focusing on CDU fault scenarios and how they protect the rack coolant envelope. The trigger for these scenarios involves executing one approved event, such as pump loss, controller loss, communication loss, or leak zone activation. The expected response is crucial. First, the fault must be correctly identified. Then, standby or fallback systems maintain the required coolant service to avoid any disruption. Additionally, leak responses should effectively limit the affected segment, just as they were designed to do. Throughout this process, rack and loop temperatures and pressures remain controlled to ensure system stability. We also need to watch for potential issues like AB power sharing an upstream single point, closed valve deadheads that could harm the pump, leak alarms preventing excessive damage, and delays in DCM or BMS alarms compared to local events. Evidence of proper operation includes monitoring loop flow, differential pressure, temperature, pump and controller states, leak zone events, and rack telemetry and recovery data. Finally, we accept the scenario only if there is no uncontrolled leak, cavitation, thermal excursion of the rack, or hidden residual isolation, ensuring the system's integrity is maintained. On this slide, we focus on the crucial step of common mode analysis before conducting fault injection. The key idea here is to avoid uncovering a shared dependency by inadvertently causing an unsafe full-site failure. We approach this methodically, examining several domains where hidden common modes often appear. For power, this means checking if both pumps or controllers rely on the same panel or UPS, and carefully tracing the single-line diagram to confirm staged source isolation. Hydraulics require close attention to shared components like headers, bypass, or isolation valves. We perform a PNID walkdown along with valve-proof and bounded flow tests to ensure safety. In controls, shared elements such as sensors, servers, gateways, or time sources are tested through signal or path injection one domain at a time. For heat rejection systems, we isolate cells or run controlled capacity tests to confirm independent operation. Finally, the physical domain demands inspection of flood, fire, access, or maintenance routes that might impact both paths simultaneously. Evidence of proper separation and approved scenarios are crucial here. Overall, this safer-proof approach helps identify hidden dependencies without risking a complete site failure, ensuring reliability and safety before moving on to fault injection. On this slide, we're focusing on Tier 3, or Rated 3, data centers and their requirement for concurrent maintainability. The key idea here is that any planned isolation during maintenance must leave a complete service path with enough capacity to support the protected load. For example, when maintaining the chiller, you isolate and drain it for service, but you must preserve the duty by keeping the system running smoothly elsewhere. Similarly, maintaining the pump involves ensuring standby flow is available and maintaining remote differential pressure control. Power path maintenance requires an alternate power source with no control reboots, so operations continue seamlessly. Controls need redundancy, both in controllers and networks, and the ability to operate in local mode if necessary. When working on rejection cells, the remaining ambient capacity should be sufficient to handle the load. And finally, when returning equipment to service, the lineup must be controlled carefully with no residual impairments. All of these steps must follow an approved method of procedure, ensure the load is protected, be backed by evidence, and include full restoration, which defines true concurrent maintenance in these facilities. On this slide, we're focusing on the key features of a Tier 4 or Rated 4 data center infrastructure. The main idea here is fault tolerance and separation to ensure continuous operation. What that means is, if there's a single failure, it must not interrupt the protected service or cause a cascade of problems across independent systems. We have two independent paths here. Path A provides power, controls, and cooling services, all separate from Path B, which is an active service path. This physical and logical separation ensures that even if one path experiences an issue, the other remains unaffected. Capacity is designed so that if a component fails, it can be removed without causing overload on the rest of the system. Additionally, automatic response mechanisms eliminate the need for manual intervention to prevent any service impact. Most importantly, the system is built so that any faults are contained. There's no cascade effect, with protections and controls designed to isolate the event. The fault-tolerant outcome here means that a single failure leads to no critical impact, provides clear evidence of the issue, and allows for safe restoration, keeping services reliable and secure at all times. In this slide, we focus on the fire mode IST, which must preserve life safety without creating uncontrolled thermal risk. The trigger for this mode is the initiation of one approved fire alarm cause and effect sequence when a cooling load is declared. As a result, fire and smoke control outputs must align perfectly with the predefined matrix. Cooling equipment should switch into the approved fire mode seamlessly, while emergency power and system monitoring continue to function correctly. Additionally, security features like doors and operator indications need to remain synchronized with the fire alarm system to avoid confusion or delays. It's crucial to watch out for any unintended consequences, such as shutdowns in unrelated cooling zones, conflicting commands between the building management system and fire alarm system, or smoke damper feedback mismatches. Restoration processes should also be carefully managed to prevent inhibited alarms or lingering overrides. We verify effectiveness through records from the fire alarm system, the status of fans, dampers, and cooling units, as well as room pressure and temperature readings, along with operator actions and resets. Ultimately, the test is accepted when the life safety function operates correctly and the plant state matches the approved fire strategy. On this slide, we focus on the critical process of blackout and black start testing, which requires explicit lubrication and restart permissives. The main trigger here is to execute an approved total power loss or dead bus scenario at a representative load, simulating real conditions. We expect the control and telemetry systems to either ride through the event or provide a deterministic restart. It's essential that the generator and switchgear sequences operate correctly, and that pumps and fans establish their prerequisites before the chillers come online. A key safety point is ensuring compressor oil lubrication and anti-recycle permissives are satisfied before restart. Watch out for common issues like a fast restart before the OEM lubrication conditions are met, all motors restarting simultaneously, chillers starting without verified flow, or manual interventions that mask the automatic sequence. To verify performance, we examine evidence such as power quality monitoring and breaker chronology, the generator and load sequence, pump flow data, chiller permissives, and thermal excursions with recovery profiles. Ultimately, acceptance means the plant restarts safely in the approved order, protecting the thermal load and strictly adhering to OEM safety constraints without overrides. This careful coordination ensures reliable and sustainable operation after a blackout event. On this slide, we see how the resilience matrix connects every claim about system reliability to tangible proof. No resilience statement is accepted without either a test record or an approved design justification. For example, when we claim redundant capacity, the required proof is the ability to remove one component while still maintaining the necessary duty. Typical evidence for this includes monitoring states, capacity, temperatures, flow, and alarms. For independent paths, proof involves showing that a fault in one path does not disable the other, backed by topology diagrams, separation details, event chronology, and load continuity records. When it comes to maintainable controls, we need assurance that controller, network, and power maintenance can occur without loss of service. This is supported by failover logs, local fallback options, and operator alarms. Fault tolerance means that a single event should cause no unacceptable impact or cascade, which we verify through automatic response mechanisms, protected loads, and recovery data. Finally, operational readiness requires operators to be able to diagnose, isolate, and safely restore the system, demonstrated through drills, standard operating procedures, competency certification, and as-left records. This matrix ensures that every resilience claim holds up under scrutiny. Restoration is not just an afterthought. It's a carefully commissioned sequence that requires our full attention. Many incidents actually happen during the transition from the protected failure state back to normal operation. First, we need to confirm that the protected state is secure, with load stable and the event contained. Then, authorization must be granted by a named control and switching authority. Next, we return the asset or path following the OEM and method of procedure sequence. After that, we rebalance flows, temperatures, staging, and roles to ensure optimal system performance. It's essential to clear any temporary actions like overrides, inhibits, and bypasses. We then verify that alarms, trends, and redundancy systems are fully restored. Finally, the process concludes with closing the issue by documenting evidence and lessons learned. Each step is vital to a smooth and safe restoration. On this section, we're focusing on evidence, handover, and operational readiness. This covers everything from raw data and reports to system manuals and competency requirements. It's crucial to ensure that all evidence is accurately documented and handed over effectively to maintain operational continuity. We also look at recurring proof and emphasize continuous improvement to keep our processes efficient and reliable. This approach guarantees that teams are prepared and systems are fully ready for operation at all times. On this slide, we focus on the crucial principle that raw evidence stays immutable and findable. This means that from the moment data is captured, we follow strict rules to ensure its integrity and traceability. First, during capture, we record essential details like the system involved, the scenario, timestamps, and who recorded the data. Then, to protect the data, raw files are set to read-only and never overwritten, preserving their original state. We apply a consistent naming convention that includes the date, commissioning level, system, event, asset, and version, which makes tracking and retrieval straightforward. Indexing further organizes the data by points, intervals, start and end times, and instruments involved, creating a precise map to the original information. Any plots generated derive directly from this raw data and remain linked back to the source for transparency. Finally, everything is archived with comprehensive information about settings, software versions, and witnesses, ensuring a complete and reliable record throughout the commissioning and testing process. The commissioning report is essentially a decision record that plays a critical role in the project lifecycle. It must clearly explain what was tested, what the measurements mean, and importantly, what residual risk remains after testing. The report is divided into several key sections. First, the executive summary provides the scope of the commissioning, the acceptance status, major findings, and any residual risk. This section enables the owner to make an informed go or no-go decision. Next, the process and governance section details the levels of testing, tags, witness involvement, safety considerations, and issue control, demonstrating that everything was executed in a controlled manner. The system results segment connects the evidence to the design intent by showing testing criteria, methods, key data, and pass or fail outcomes, along with any deviations. Then, there's a scenario chronology that outlines triggers, automatic responses, operator actions, and system restoration. This proves the system's resilience and operability under various conditions. The evidence index includes scripts, raw data files, screenshots, certificates, and photos, which together make the report's claims auditable. Finally, any open issues are documented with details on risk ownership, mitigation measures, expiry dates, retesting plans, and closure strategies to clearly make residual risk explicit. This comprehensive approach ensures transparency and supports confident decision-making. This slide highlights the crucial role of the system's manual in bridging the gap between design, testing, and practical operations. Unlike O&M manuals, which focus on individual equipment details, the system's manual explains how the entire service is expected to perform and interact in real-world conditions. Starting with design and configuration, it includes the operational requirements, basis of design, system boundaries, and detailed schematics. It also outlines different lineups for normal, maintenance, and failure scenarios, along with set points, limits, and as-left configurations to ensure consistency. On the operations side, it covers the sequence of operations, alarm philosophy, standard and emergency procedures, controls architecture, and local fallback options. It emphasizes comprehensive monitoring and access to trending data and evidence to support effective management. Finally, from a lifecycle perspective, the manual documents preventive maintenance tasks, spare parts, service agreements, commissioning records, and historical issues. It also provides a test matrix for seasonal or recommissioning activities, as well as training records and identification of competency gaps. This holistic approach ensures smooth, reliable, and predictable operation of the data center MVAC system. On this slide, we focus on the crucial concept that competency sign-off is performance-based, not just about attendance. Simply being present doesn't prove that operators can effectively protect and recover the service. Instead, competency is demonstrated through a series of specific, practical actions. For example, operators must clearly explain the system topology and trace heat and controls through both normal and failure conditions, supported by walkdowns or marked-up schematics as evidence. They need to operate the system by executing approved start and stop procedures, whether local or remote, with observations recorded on checklists and confirming the as-left state. Diagnosing faults is another key competency, using alarms and system trends to identify simulated issues, documented through investigation records and proper escalation. Isolation skills require applying MOP and LODO boundaries without disrupting protected duties, demonstrated through permit simulations and peer checks. Recovery is tested by responding to scenarios like high temperatures or equipment loss, evaluated through drills and timing notes. Finally, operators must be proficient at using documentation, finding critical procedures and settings independently to support safe and effective operations. This performance-based approach ensures operators are truly ready to maintain and restore system integrity under real-world conditions. Ongoing commissioning is essential to preserve the proven state of a data center's MVAC system. Over time, baseline drift, firmware changes, sensor degradation, and phased fit-out can all cause the original commissioning evidence to become invalid. To manage this, we start with an accepted baseline, which includes trends, settings, and configurations. Then, we continuously monitor key performance indicators, alarms, drift, and maintenance changes to catch any variations early. When specific triggers occur, such as seasonal shifts, load growth, or repeated issues, we conduct targeted retests to gather calibrated evidence. This process allows us to compare the current state with the accepted baseline and facility requirements. Finally, the resulting updates to manuals, training, and the risk register ensure the system remains reliable and well documented. On this slide, we focus on Practical Lab 1, where the main objective is to map a complete cooling train from the design intent through to CXL6 evidence. To achieve this, we start with key inputs like the approved schematic and ESCO, the asset register list, CX gate definitions, and the resilience target. These inputs are crucial because they form the foundation for accurate mapping. Then, the tasks involve defining boundaries and interfaces, assigning tests and hold points, naming measurement and evidence owners, and identifying any missing or duplicate scope. The expected outputs are a concise, one-page evidence matrix, risk-ranked gaps, and a clear witness and sign-off plan. Ultimately, the goal is to ensure that every critical claim is backed by an acceptance criterion, a calibrated measurement, and a restoration record, ensuring a thorough and reliable commissioning process. In this practical lab, our main focus is to reconcile an HLT heat balance. The objective here is to determine if the measured cooling result is credible and to explain any residual discrepancies. To do this, we start with several key inputs: the load bank kilowatts broken down by zone, chilled water flow along with the matched temperatures, auxiliary power, and sensor uncertainty data over time. These inputs allow us to calculate the waterside heat accurately. Next, we combine measurement uncertainties to understand their impact on our results and assess any stored energy or transient effects that could influence the heat balance. It's crucial to interpret any balance errors carefully, as they guide us on the necessary next checks to ensure accuracy. The output of this process includes a detailed calculation sheet, a clear statement of uncertainty, and ultimately a pass, hold, or retest decision. Here, we have a pass decision, supported by consistent units, reasonable assumptions, measured uncertainty, and time-aligned evidence, confirming the reliability of our heat balance. For Practical Lab 3, our focus is on running a chiller or pump failure integrated system test, or IST. The main objective here is to execute one controlled failure, starting from the pre-brief all the way through to full restoration. To do this correctly, we'll need several inputs: an approved scenario and method of procedure, a stable representative load to test under realistic conditions, a trend list and abort criteria to monitor the system, and clearly named test and switching authorities to manage the process safely. The tasks we'll perform include capturing a baseline of system performance, triggering one approved event, then closely observing the automatic responses. After that, we hold the system steady, restore it to normal operation, and verify that everything is functioning correctly. The outputs expected include a detailed event chronology, thermal and hydraulic plots, records of any issues and retests, and assigned as left confirmation. Ultimately, for a pass, protected duty must remain within all criteria, with no cascade failures, hidden overrides, or residual impairments left in the system. This ensures the system's reliability and safety after the test. Commissioning truly succeeds when the evidence can guide operations. It's not just about collecting certificates and checklists. The ultimate goal is to deliver a facility that can be reliably operated, maintained, diagnosed, and recovered throughout its life cycle. First, we need to prove the physics, ensuring that heat follows a measured path, that capacity and control margins are clear and explicit, and that both normal and failure states stay within approved limits. Next, protecting resilience is key. Maintenance activities and fault conditions must be treated as separate tests to avoid hidden common mode or cascading failures. It's essential that local safety and fallback boundaries remain intact at all times. Finally, preserving the proof means that raw evidence is synchronized, traceable, and trustworthy. Operators must be competent, with procedures that are practical and usable. Any changes must trigger targeted recommissioning, and critically, no gate can advance if there's an open safety-critical defect, invalid evidence, or unsigned restoration. This approach ensures a robust and dependable data center MVAC system.